Hello and welcome to the third video for this lecture series for the class of ATMO 412. In the first two videos, we talked about the fundamental dynamics of the atmosphere. We introduced some of the fundamental concepts that we're going to use, such as vorticity and the Navier-Stokes equations and the thermodynamic equations. And in the second video, we talked about the QG approximation. We looked at the basic assumptions that are used. We looked at the equations that can be derived. Today, we're going to introduce another important tool that is isentropic analysis. And this is something that could be useful in many cases, for example, in which QG approximation doesn't really hold, or cases that are a bit more complicated. QG approximation is great, don't get me wrong. It's a wonderful approach to do weather forecasting, but there are some drawbacks to this approach. One of them is the fact that the Laplacian that is on the left-hand side of both the omega and the high tendency equation, the Laplacian is really hard to invert. If you want to solve these equations numerically, you have to invert a Laplacian, and there are many algorithms to do that, so you don't have to start from scratch, but these techniques can be computationally very expensive, particularly if you're dealing with very rich data sets, such as the ones in meteorology. And the second thing is that the QG approximation is very restrictive in many regimes, right? And so you have to have a small Rossby number, you have to neglect friction and orography and yada, yada, yada. And there are many times in which you have situations where QG doesn't really work and you have to use something else. And if you have a really powerful supercomputer, then maybe you have no problem. But if you want to get a quick understanding of what is happening just by looking at a weather map, then maybe you want to use some different tool, right? Okay, so in order to introduce this tool, I want to start from the basics. And in particular, I want to start from the first law of thermodynamics. I'm sure you all remember it. It's a law that relates the internal energy of a system with the work that the system does or that is done on the system, and the heat that is exchanged between the system and the world around it. If we consider a situation where there is an adiabatic system, so heat can be ignored, the first law of thermodynamics can be expressed by this very simple formula here. I'm sure you'll remember that starting from this formula, it's possible to define a variable called potential temperature. We talked about this on the first video of the lecture, and we like potential temperature for all kinds of reasons. One of the things that we like potential temperature for is that it can be shown that the logarithm of this potential temperature, modulo constants added or multiplied, this equals the dry entropy of a parcel. So if you have a parcel that does not contain too much moisture, let's put it that way, and that is dry, so there's no condensation or whatnot, the entropy is equal to the logarithm of the potential temperature. And so when we consider lines that connect points that have the same potential temperature, given that the logarithm is a monotonic function, then these lines must also have the same entropy. That's why lines of the same potential temperature, they're known as isentropes. Okay, and as you probably figured by now, these are going to play a big role in today's class. Why do we like all of this? Well, we like it because dry entropy and potential temperature are conserved for adiabatic motions. Again, we're neglecting moisture for now. But so imagine that you have an air parcel on a given isentrope. So this one is a parcel at a 310 Kelvin isentrope. We may not know exactly what's going to happen to this parcel dynamically, but what we know for certain is that this parcel has to move on this surface. Okay, so time t0, it starts here. T0 plus delta t is here. 2 delta t is here. We didn't know this to begin with, but we knew that it was confined to stay on this isentrope. Okay, So we really like any kind of conservation law because it helps us reduce the dimensionality of a problem or of a system that sometimes can be kind of overwhelming. So now within this system, consider a small fluid element, and let's say that this fluid element is between two isentropes, okay, of temperature theta 1 and theta 2, for example. Then we can write this element, we can compute the mass of this element, and this element can be expressed as a function of delta theta, okay, the spacing between the isentropes. So if we start from the mass is simply the density times the volume. We use the hydrostatic approximation, so this can be rewritten in this way. And with some manipulation, we obtain something that we call the isentropic density. The isentropic density will be useful later on in the lecture series, but for now you can think of it as the equivalent of density, but when we consider theta as a vertical coordinate, okay? Notice that this isentropic density is inversely proportional to the static stability. Static stability is d theta dp or d theta dz, again, hydrostatic approximation, and so this is the inverse of that, and so it's, the density is, in a certain sense, a close cousin of the stability itself. Okay, so how do we use isentropes to say something about the atmosphere? Well, let's start from some sqt log p, okay? This is a simple case from 2002, January the 3rd. This is taken in North Carolina, it doesn't really matter. And the black line here is the dry bulb temperature, and this is the dew point temperature in blue. So you start from here, and at a given point, because you know the temperature and you know the pressure at that point, you can certainly compute the potential temperature, right? This is not a problem. If you're at 1,000 hectopascal, so right near the surface, this is a very simple exercise because temperature and potential temperature are equal, but at any given height, you can compute that. No problem at all. Once you compute these potential temperatures, you can connect different points in space. So you can do this analysis for every single station that launches Roentgens, and you can then connect the same isentropes. And if you do that, let's say that we pick the 296 Kelvin isentropes, but if you do that, you might get to the point where you have a map like this. What is this map representing? Well, given an isentropic value that we decided, so 296 Kelvin, this is telling you at which pressure that potential temperature is achieved, okay? Remember that in general, potential temperature increases with height, right? And so here in this case, for example, we start from Florida. This is telling us that these lines, they all have obviously the same isentrope, and these values of isentrope are found at 900 hectopascals. This is telling us that over here in Canada, the 296 Kelvin isentrope is found at 500 hectopascals. This also kind of makes sense because, obviously temperatures are colder as we move north. And this you can interpret, you can see that it looks very much like, this looks like a trough, right? This looks like a pressure surface, and it looks like we're looking at geopotential heights. And in many ways, these are very similar, okay? And so we can interpret these just like we interpreted the geopotential heights on a given pressure surface, okay? And I'll tell you even more. If you define this function that is called the Montgomery string function, this is very similar to a concept that we call dry static energy. So it's a combination of the internal energy and the potential energy of an air parcel. If you define this on your isentrope, then the derivative in the zonal and meridional direction, these are the geostrophic wind components on the isentrope, okay? And so this further shows how much the isentropic analysis and the geostrophic analysis are, in a sense, correlated, okay? So for the geostrophic analysis, we had lines of constant geopotential height, and we were looking at isobaric surfaces and lines. Here, we're looking at isentropic surfaces, and we're looking at lines of constant Montgomery string function. You can certainly compute this, and this is something that is likely related to, again, to the entropy and a close cousin of potential temperature. And if you take these derivatives, then these give you the components of the geostrophic wind, much like you did with the geopotential heights. Okay. The other thing that we can use is that now we can write down the simple equation of a total derivative of pressure in the case of a given isentrope, and you can show that the total derivative of the pressure is related to three different terms. So this goes without saying, the total derivative of pressure by definition is omega, right? Is the pressure velocity that we've been sort of looking at for the past few lecture series, for the past few lectures. The first term that makes up this tendency over here, this is a local temporal tendency. So this is a term that is given by local changes of pressure. And these might be due to a variety of reasons. I don't know, local pressure changes for whatever reason. Maybe there's, I don't know, some effect from the surface that forces pressure to change. Who knows, right? But this is something that can certainly happen, no problem. The other term is an advective term. This is a pressure advection term. And this is a term that we are interested in because it is a dominant term in many, many situations, right? And so this is telling us that if there is a gradient in pressure on an isentropic surfaces, then this is likely associated with ascent or descent. So in particular, if wind is directed from higher toward lower pressure on an isentrope, then there's going to be a rising motion. If wind is going from lower pressure toward higher pressure, then there's going to be descent. Okay? And as I said, remember, this is very often the important term that we want to take into account. Okay? So we want to look at wind crossing different isentropes, if you will. Different isobars on an isentropic surface. And the third term, this is due essentially to changes in theta over time. And these are any kind of diabatic processes. So an example would be if you have a complicated system, like an extratropical cyclone, and this system releases a lot of latent heat, or there's a lot of cooling due to rain evaporation. It could also be radiative processes, right? So any kind of diabatic term that would cause a change in temperature, this would cause a change in the sort of ascent. This would cause either ascent or descent of the isentrope. So take an example over here, for example, and we have an isentrope that is 300 and a higher isentrope at 310 Kelvin. And let's say that there is some kind of latent heat release and some kind of evaporative cooling below it. Let's consider the latent heat release over here. So latent heat release means that this point over here is going to get warmer, right? The temperature is going to increase because latent heat is released, and this means that the molecules at that point are going to move faster, or in other words, the temperature is going to be higher. But so that means that the isentrope, the 310 isentropes, must be descending over here, right? Because the temperature is increasing. So this corresponds to this point in space now is going to correspond to a higher isentrope. And so the isentrope at 310 is going to lower. So there's going to be a descent of the isentrope over here. On the other hand, over here, this point is going to cool down by evaporation. And so the temperature here is going to decrease. So that means that the isentrope over here must be lifting, right? Because this is getting colder now. And so it's going to belong to an isentrope that was lower in altitude. And so this isentrope is going to get lifted. So the result is that these 2 points are going to be sort of squeezed together. But the point here is that latent heat release over here, given that there is a stratification, right? In theta, this is going to cause the isentrope to descend, and this is going to cause the isentrope to ascend. Okay. Okay, so the problem with this equation is that there's this dp dt that is sort of a wild card, because who knows what the local pressure tendencies might be. All right. But so there's an approximation that is called a frozen wave approximation that comes to our rescue, and that allows us to get rid of that term, even though we must pay for that approximation in some other way, and we'll see in a minute. So let's assume that for now we're considering some variable, okay? And let's say the variable is S, okay? And we're assuming that any local change in this variable is due to the motion of some kind of synoptic scale weather system that is moving through, let's say a deep trough, okay? And this trough is the only thing that is causing the change in this variable, okay? Let's also assume that the system is not really rapidly changing shape or speed. So we have, imagine this trough that is coming through. Let's see if I can find a trough. Imagine a trough like this that is coming through and that is moving eastward. And imagine that the speed remains the same and that the trough maintains the same shape, okay? Then for this scalar variable that you defined, you can show very simply that the changes, obviously the total derivative, if you follow the system, is 0, which means that any local change in this variable must be compensated by changes due to advection. And the advection here is dominated by C, and C is the phase velocity of the weather system. Okay, so you have this wave that is quote unquote frozen. So it's translating, in our case, to the east, and it is frozen. It's not moving. It's not changing. It's moving, but it's not changing shape. It's not changing speed. Okay, so if you follow this, then any local change at a given point in space, I don't know, North Carolina or New York or Montana or what have you, must be due to the advection, okay, to this advection term. Okay, so I hope we're clear on this. But at the same time, because we didn't specify which variable we were going to choose, you could pick, as your variable, you could pick pressure. But if you pick pressure, then this means that dp dt over here must be equal, roughly, to minus c dot delta p, okay? And this del over here, this is the gradient over an isentropic surface. And so if you put the two things together, right, if you put that, this becomes minus c dot gradient p, then you can put these two things together, and this gives you v minus c dot gradient p plus the diabatic term. So in other words, if we're assuming that we have a synoptic system and that any change that we observe in a particular variable, and in this case in pressure, are given to the movement of this weather system, and we assume that this weather system maintains its shape and its speed, then the pressure velocity can be rewritten at a given point, and it can be rewritten as a combination of two things. And notice how nice it is that this was also true in the QG approximation, that any equation can also be, is always written as a sum of two terms, right? There's the differential vorticity advection and the thermal advection. And here it's the advection, of this pressure gradient, of pressure, and the other term is a diabatic term. We're paying now because now we have this minus C, right? So this is motion relative to the trough or to the weather system that is moving. And so we simplified our lives because we don't have the dp/dt, but now the tricky thing is that you have to estimate C, right? Whenever you have some system. And in some cases, C might be a small term, right? So maybe you have a very slow moving system. And so you can forget about C and you could just focus on the advective term and the diabatic term. And this was also the same as saying that the local pressure tendency here was negligible, right? If you have something that is not moving, if you're accepting that changes in pressure are due to the movement of this system, and you're saying the system is not moving really fast, then you can also ignore the changes in pressure, okay? So it's another way of saying this. But unfortunately, in many circumstances, you cannot neglect this. And estimating C can actually be pretty hard for a variety of reasons. First, these synoptic weather systems are not rigid, right? And air is compressible. And so when you consider a trough that is moving, the trough, first of all, is not going to maintain its shape, right? We talked about, if you remember the high tendency equation and the QG approximation, that had these two terms, and God knows what advection is going to look like, what differential thermal advection is going to look like, or what the cyclonic vorticity advection is going to look like. Might be that one part of the trough is advecting in one way, the other part is advecting in the other way. And so this will give a trough that moves at different speeds at different points in time, first of all. And second, how do you really assess the velocity? I mean, it's not like you have a small particle that you're following with a camera, right? And you can take pictures. You have this really complicated system that typically spans hundreds, if not thousands of kilometers. What you decide is the point where you derive the speed, where you compute the speed. What saves the day for us is to remember that we're using this as a simple, as sort of a simple diagnostic tool, something to obtain a qualitative understanding of the system. So we're not, our lives are not going to depend on these estimates, and we can use calculators for those. This is just to get some intuition of what might be going on. So an approximate estimate of this term might be sufficient in many cases. So here we have an example of a system that affected the southeastern U.S. Notice the date. This is January 3rd, 2002. And if you remember from a few slides ago, this is exactly the time when this Rhine-Sonde was taken, and this is also the time when this was computed. I jumped. This is showing over here, the blue lines are showing the 500 hectopascals geopotential height, and the absolute vorticity is shaded, right, with the values here in the legend. Notice that we have this trough with the minimum here. And just to reiterate, if we go back to this, not bad. The trough with the minimum. So isentropes, pressure analysis on an isentrope, and geopotential heights, they're close cousins, okay? And here is the same map, but instead of showing the vorticity, we're showing the sea level pressure. What's the point for doing this? Well, this is a tricky situation because over here we have advection of cyclonic vorticity, right? I mean, this is pretty strong cyclonic vorticity. There's a maximum over here. And so if you're considering the minimum of the trough here, we're advecting a lot of cyclonic vorticity. So that would suggest that we have ascent over there. let's assume that we're not really advecting any vorticity near the surface, and so this is differential vorticity advection, right? So we're happy with as far as the QG omega equation is concerned. And now we look at this plot over here and notice that this area here where you have the cyclonic vorticity advection, this is, it has a high at the surface. And so this is, for what we know about the, for what we know about geostrophic motions, we know that we're expecting cold advection over eastern Texas, okay? And so we have differential cyclonic vorticity advection, ascent, but we also have cold advection, which would force descent. So simple QG omega, not good here. So we need to resort to the Q vectors. Okay, well, let's look at the Q vectors. If you look at Q vectors, we noticed something interesting, and we noticed in particular the vectors are shown here, and the dashed blue contours imply convergence, and the solid red imply divergence, right? And so these often solve the Q vector and the convergence or divergence often solve ambiguous situations, right? And so we find that over here we have pretty strong ascent on the East Coast, but over here, eastern Texas and sort of Arkansas, Louisiana area, the Q vectors suggest that there is pretty strong ascent over there. However, if we then go and look at the omega field, so the pressure velocity at 700 millibar, which is sort of right above the boundary layer, this is showing pretty strong ascent over here. I believe this is where the Carolinas are, more or less, so pretty significant ascent over here, but almost nothing over here. So the Q vectors and this are not really in agreement, right? We don't really see a strong ascent over here, okay? And we could now turn to the isentropic analysis. And if you do that, this is showing, again, we're focusing on 296 Kelvin isentropic surface. And this is a surface that lives pretty low in the atmosphere. And so it can be useful sometimes to figure out what is going on. And this is similar to what I showed before, the one that we saw early on over here, okay? And this is superimposing the analyzed isentropic winds, okay? And if you follow the method that I discussed before, so if you look at where winds are crossing isobars in this case, then you'll have to conclude that there's going to be, well, strong ascent over here or the Carolinas, so the eastern Florida and the Carolinas, but you should also conclude that there's going to be ascent over here, right? So this is corresponding to what the 700 geopotential, 700 millibar omega field was saying, but you should also conclude that you're going to have some ascent over here. However, if you now compute if you remember the frozen wave approximation, it's not the advective term itself that matters, but it's the advective term with respect to the motion of the system. So if you remove the velocity of this trough, that phase velocity of the trough C, and you recompute the velocity field, then you see that there is going to be now weak ascent over Mississippi and Alabama, strong ascent over the Georgia and Carolina regions, this we knew, but now we see weak ascent over the eastern Mississippi and Alabama region, okay, which is more in line with what the pressure velocity over here was showing, okay? So we have a case in which the QG analysis, for whatever reason, maybe the ageostrophic component was too strong, the QG analysis kind of fails. But if you follow the isentropic analysis and you were able to compute the storm velocity or the trough velocity and remove it and redo the analysis, then you find that something that is much more in line with what is actually then observed. And another useful piece of information, if you want to know what's going on, is adding, in this case, they're adding the mixing ratio of water vapor on the isentrope. And notice that there's a pretty high mixing ratio over here, and this water vapor is being advected into this region. And if you then look at the rate of reflectivity, this then corresponds to the snowstorm that was observed. So strong ascent, advection of water vapor through this wind over here. This is causing this over here. If we hadn't, and there's really weak ascent over here, but really, really weak. If we hadn't done this and we had followed the picture that we were showing earlier, particularly if we had looked at the Q vector, but if we had looked at the absolute velocity and not the storm relative velocity, we'd have gotten the completely opposite picture of what happened. So these were going in this direction, but if you look at the storm relative, it's very, very weak ascending motion, okay? Okay, I wanted to conclude just by talking about the adiabatic approximation. So, as usual, whenever we look at storm motions, whenever we looked at motions in the atmosphere, we have to make approximations. We have to approximate the motions as being quasi-geostrophic. In this case, we're approximating the motions as being adiabatic. And this is not always true, right? Whenever we have ascent, typically this ascent will cause the release of latent heating. And this heating is diabatic. And so this means that the parcel is not moving along an adiabat anymore. However, if we consider, there's two things that we want to say. One example is a parcel that is rising, and let's say it rises over a dry adiabat, and then at some point it condenses, and this condensation makes it grow along a moist adiabat, okay, not a dry adiabat anymore, which is what we use to define the isentropes. This parcel is the qualitative behavior of the parcel is still the same. Quantitatively, this parcel is crossing a number of isentropes, but qualitatively, it's still ascending. It's still doing the same thing. And so, if anything, the isentropic method is providing, let's say, a lower bound. Okay, so this parcel should go like this. As a lower bound, this is not bad. Okay, the parcel actually grows much higher, but as lower bound, this is not too bad, and it's not a bad estimate to have. And the second thing is that, related to this, the reason why we introduce the isentropic analysis is to derive a qualitative understanding of what is going on. So as long as qualitatively things add up, then we're happy. What we care about here, maybe it's not so much whether the parcel goes to, 210 Kelvin or 220 Kelvin or 230 Kelvin isentrope, but the point is the parcel going up or down? Because if it's going up and there's a lot of water vapor, then you can tell your parents that it's going to rain soon, okay? So yes, there are approximations, and these approximations are almost always violated because otherwise our job will be too simple. But that's not necessarily a bad thing, okay? Much like QG approximation, in many cases it's violated. And it's a very restrictive set of approximations to adopt, right? Because there are mountains, there's friction, there's whatnot. But that doesn't necessarily mean that we have to throw away everything, okay? As long as we're happy with a qualitative understanding of things, then we're good. Okay, so I want to conclude this brief lecture, and I want to conclude it just by presenting some, pros and cons, I guess. To me, the most important pros are that the isentropic analysis is really simple conceptually. It takes a little while to get used to, how the surfaces intersect each other and what you're visualizing, that, you're now, before we were on a surface of constant pressure, we were looking at geopotential heights, and now we're on a surface of equal temperatures, and we're looking at this weird Montgomery string function. But once you get used to that, it's actually pretty simple, and conceptually is not that hard. And, if wind crosses an isobar, there's going to be ascent, or there's going to be descent, depending on how it crosses it. The way that this allows you to see a parcel is very intuitive. You can grasp the meaning of this right away. The adiabatic assumption is not great, but it's good for most of the time. So, there are storms on Earth, but by and large, you can be happy, and particularly if you're happy with a qualitative understanding of how things are. And also, this does not require stringent approximations like small Rossby number or horizontally uniform static stability. And it's far less restrictive in many ways than the QG approximation. So when QG fails and it doesn't give you the right answer, or it gives you some ambiguous answer, isentropic analysis is your next best bet, I guess. Obviously, there are some, drawbacks, and we have to be clear and honest about those. Diabatic processes, in some cases, that can be pretty significant, right? So if you're looking at a map and you're concerned about some kind of a weather system, chances are good that something's happening in this weather system that is not adiabatic heat exchange. That is not an adiabatic process, So there's some kind of diabatic heating going on. So what's going to happen then? Well, maybe in some cases when it's really, really useful, you don't know. This doesn't give you any dynamical interpretation. So we don't know why things are happening in a certain way and what's causing what. All we know is what's happening now given what's happening now, right? We can diagnose omega knowing pressure now, but this doesn't contain any prognostic approximation, doesn't contain any mechanistic understanding. We're kind of tacitly assuming that theta increases with height monotonically, but unfortunately, theta is not like height or pressure. Theta can be really complicated, and so theta can be non-monotonic, and when that happens, then it's kind of tricky. If you have multiple points in a given air column that have the same theta, then what are you going to do? What do you join? How do you connect this to other values of theta at other points? Do you connect the topmost, the bottom, the other ones, right? And also, isentropic surface heights, they're certainly not as constant as altitude, and they vary a lot more than geopotential height. So they vary with season, latitude, and they also vary with what kind of phenomenon you're examining, right? So if you're examining something that is heating up real fast, something that is pulling down air real fast or whatnot, they can change a lot more, and they can be way more variable than other means like geopotential heights that we talked about the other time. Okay, so this concludes pretty much what I wanted to say about isentropic analysis. Next time, in the next video, we will look at potential vorticity And in particular, we will look at how, again, we can look at potential vorticity as another means to gain some information about what is going on. As usual, I'm available for any kind of question, so please don't be shy. Reach out with an email, and I'll be happy to answer any of your questions, and we can talk about more of this in class. Thank you.